So if you've ever written a SQL query, you've dealt with a database's logical design. But have you ever stopped to wonder what's really happening under the hood? How the database actually stores and pulls that data from a disk? Well, today we're going way beyond the select statement. We're heading into the engine room to check out the architect's playbook for building truly high-performance systems.
So let's start with the big question. What really separates a good system from a great one? I mean, a good system will give you the right answer, but a great system, it also gives you the right answer, but it does it in milliseconds, even when you're dealing with billions of rows. The secret to making that jump from just good to truly great, well, that all comes down to its physical design. So let's just draw a really clear line in the sand here. On one side, you've got logical design. That's all about the what. What are your tables? What are your columns? How are they related? Its number one goal is just correctness. But then you have physical design. That's all about the how. How is that data actually arranged on the disk? And its goal is pure, unapologetic performance. You absolutely cannot have a great system unless you master both. And the funny thing is, the core idea is actually super simple. Just picture a library. If every single book was just thrown into one giant pile in the middle of the room, finding anything would be a total nightmare, right? But organize them by subject, and suddenly you can find any book you want in just a few seconds. That intelligent arrangement, that is physical design. It's really as simple as that. Okay, so to put it a bit more formally, physical design is the whole process of deciding how your data is physically laid out on a storage device. And this one decision has this huge ripple effect on literally everything else, from how fast your queries run to how well your system can scale when the data starts piling up. All right, let's get into our first major tool in the architect's playbook, and believe me, this one is a game changer. It's called partitioning, and it's all about taking something massive and breaking it down into manageable pieces. Probably the easiest way to get your head around it is like this. Imagine you had one giant, 1,000-page notebook for all of your school subjects. It'd be heavy, clumsy, and just impossible to find anything. Well, partitioning is just the simple act of splitting that mess into separate, smaller notebooks. One for math, one for history, another for science. Easy. So in database terms, partitioning means we split one logical table, that's the one you see when you write a query, into many smaller physical pieces. Now, to your application, it still just looks like one big table. But under the hood, the database has smartly organized it into all these little chunks. This makes your queries way, way faster, and it also makes maintenance, like deleting old data, incredibly efficient. And you've basically got three main strategies for how to do this. First up is range partitioning. This is perfect for anything with a date or a timestamp. Think January's data goes here, February's goes there. Then you've got list partitioning. This is for when your data isn't a continuous range, but discrete values, like sales regions or product categories. And finally, there's hash partitioning. This is your go-to when you don't really care about the groups, you just want to spread the data out evenly to handle a ton of writes. Okay, now look at this query. It's about as standard as it gets, right? We're just asking for all the orders from January 2025. Now, on a normal table with billions of rows, this query could be painfully slow. But with our table partitioned by date, something kind of magical happens. And here it is, the secret sauce. The magic isn't actually what the database does, it's what it doesn't do. Because we partition by date, the database is smart enough to realize it only needs to look in the January partition. It completely ignores, or as we say, it prunes, all the other months. It doesn't even have to look at them. And hey, to bring it back to our notebook analogy, it's just common sense. If you're looking for your January homework, you're not going to waste your time flipping through the February or March notebooks, are you? The database is doing the exact same logical thing. Okay, let's move on to our next set of tools. These are all about arranging data even more intelligently inside those partitions and at the same time making it take up a whole lot less space. So clustering basically takes our library analogy one step further. It's not just about putting all the history books in the same section of the library. It's about making sure all the books on, say, Roman history are sitting right next to each other on the very same shelf. So the really crucial point here is that clustering physically reorders the rows on the disk itself based on some key you choose. That way, when you read one row, the next one you probably need is right there beside it, making your reads blazing fast. The only catch? You have to maintain this order as new data comes in. Otherwise, things start to get messy again. Now, what about making the data smaller? You've got two main flavors here. Row-based compression squeezes each individual row,
which is great for transactional systems. But for analytics, column-based is the absolute king. It takes all the values in a single column, like a country column, and compresses them all together. And because you have so many repeated values, the compression you get is just fantastic. But hold on, you might be thinking, doesn't decompressing data add extra work for the CPU and slow things down? And here's the wild counterintuitive part. Reading data from a disk is thousands of times slower than your CPU doing work. So the time you save by reading a much smaller file from the disk almost always completely blows away the tiny CPU cost it takes to decompress it. It's a huge net win. All right, so now that we've got the tools, let's go even deeper. Let's look inside the engine room at two hidden forces that our physical design choices have direct control over. You know, your choice of a primary key might feel like a logical decision, but let me tell you, it is a massive physical one. Its sequential key is awesome because all your new data goes neatly right at the end of the table. The downside, everybody's writing to the same spot, which can create a write hotspot. On the other hand, random UUIDs avoid that hotspot by spreading writes all over the place, but they create chaos in your index. We call it fragmentation, which can make some of your queries much slower. It's a fundamental trade-off you have to make. And then there's this thing called the write-ahead log, or just WAL for short. Before a database ever touches your actual data files, it first scribbles a quick note about the change in this super fast append-only log. Why does it do this? Well, it guarantees durability. If the system crashes, it can replay that log and not lose your data. It's exactly like jotting a quick note in a rough notebook before you commit it to the final, clean version. And this is where everything starts to connect. Every single physical design choice we make affects this log. Good compression? Well, that means smaller data, which means less WAL traffic. Dropping an entire partition? That's one tiny little log entry compared to deleting millions of rows one by one, which would be a huge log storm. Even your primary key choice impacts how efficiently the wall works. See? It's all connected. Okay, we've covered a lot of ground. So how do we actually apply all of this? Let's bring it all together into a simple, practical architect's checklist. When you're designing a system that needs to scale, this is your playbook. This is the thought process. First, ask yourself, is this table even big enough to need partitioning in the first place? If the answer is yes, then okay, what's the natural key? Is it time, a region, a customer ID? Then, and this is so important, can your queries actually use that key to prune partitions? After that, you can think about whether clustering might help, if compression makes sense, and what the overall read and write patterns look like. And if you ignore that playbook, you are almost guaranteed to run into one of these common mistakes. The absolute biggest one I see is partitioning a table, but then writing queries that can't prune anything. You get all of the complexity with literally zero benefit. Other classics are just blindly using random UIDs without understanding the trade-offs, or clustering your data once and then totally forgetting to maintain it. So what's the big takeaway from all this? If there's one thing to remember, it's this. Logical design is what defines correctness. It makes sure your answers are right. But physical design is what defines performance. And when you're operating at scale with millions of users and terabytes of data, physics always wins.